Hello, in this video I'm going to go through the final section of the Oxford PAT from 2006. So this is the maths section. I've already done sections A, B and C, the physics part, in other videos. So if you want to have a look at those, then scout around elsewhere or on the same playlist. So here I'm just going to go through however many it is, 10, 11, 12, I can't remember what it is, usually that sort of number of questions. Just see how we get on with these. Oh yeah, so you can't use a calculator on this one, right? So yeah, a change compared to the physics part of it. And question one shows why you can't use a calculator, because yeah, you just type all of that in. So let's go with that then. We've got difference of two squares. So it's going to be 2007 plus 2006 times 2007 minus 2006. So that certainly makes things easier. So 4013. Now we've got this, oh god blimey, 1.001 to the 6 minus 1.001 to the 5 to one significant figure rather than precisely. For that second one, so we've got 1 plus 0.001 to the 6 minus 1 plus 0.001 to the 5. So if we're just going to one significant figure, because when we expand those out, thinking of what our binomial expansion is going to do on these, the ones are going to end up cancelling. So all we care about is the difference in the next term. So let's just do two terms for each. So we're going to get 1 plus nx, so 1 plus 0.006. Then we need to take off 1 and 0.005, which is going to give us 0.001. So yeah, that's the significant figure. And we could have taken that further, but there's no need to, because we're just going to start throwing in these factors of 1 over 1,000 all over the place. So that's question one. Question two, find the gradient of the line joining the points that and that. So the gradient is the change in y divided by the change in x. So providing we keep the coordinates in order, doesn't really matter what's happening. So y has gone down by 10 and x has gone up by 1. So minus 10. That's our gradient. 3, find all values of x for which these log equations are satisfied. Right, so if we've got a log base e of e to the power something, we're just going to get 3x equals 6, x equals 2. So that's fine. The second one, okay, we're going to have to do a bit more playing around on this. So we can, well, we're saying that 3 squared is equal to x squared. So actually we don't have to do much playing around on this at all. So 3 squared equals x squared. So x is going to be equal to plus or minus 3. So yeah, you have to be wary on some of these. When you get these x squareds, there can be a temptation, if you don't go in for essentially this is the definition of what a log is. Oh yeah, well I'll pull that 2 down to the front, then divide by 2's, and then you're left with just one answer. You've thrown away one of the solutions by just chucking out this x squared bit. So yeah, you have to be careful with that when you're making that change. So yeah, going for that 3 to the power of 2 is equal to x squared is a much better approach, because you don't throw anything away. So that's first 3 done. Question 4, simplify this. Well, 5, 12 and 13 always look great because you've got a right angled triangle then. So if we've got tan to the minus 1, 12 over 5, right, let's draw our right angled triangle then. So we're going to have 13, 12 and 5. So this is opposite over adjacent for tan. So that's talking about that angle. So this bit here is just theta on our picture. Sine theta is opposite over hypotenuse. So that bit is going to be 12 over 13. And then we're multiplying it by 13, which is going to leave us 12. All good. Sketch these functions, sine squared x, and then this weird looking thing. Right, I've got a bit of space up here. So let's start. We've got sine squared x. Let's start with sine x. which is looking this sort of thing. Now, if we're going to square it, it's going to pull all of these values, that these are going to stay in the same place, ones, and because they're ones and zeros, so they're fixed. That -1 is now going to become a +1. Everything in between is just going to squeeze, and so we're just redrawing this as a something like that. Yeah, but do it on two separate graphs. But yeah, you end up with this. It looks a bit like a sine wave. You have slightly changed the shape of it, and everything is now positive. So that's what we're getting for that. And then we've got a 1/x² -1. Right, let's think about what's going on with all of this then. So we are going to have all parts of the xy plane on this. So when x is 0, you've got -1. So it's going through here at -1. When x is 1 or -1, we've got a vertical asymptote. So we've got that there at 1, that there at -1. When x is huge, then we're going to a +0. So we're going to end up over here. When x is huge and negative, we're also going to end up +0. So we're going to end up over there. Can't have that much more we need to do with this. So if x is a little bit less than -1, then we've got something huge and positive. If it's a little, when I say less than -1, so more negative, if it's slightly more positive, then we're going to get there. And then similarly, okay, right, so we can see what's going on now. So we've got that there, that there. Oops, bit wonky. It's my problem of drawing on a screen. And then that there. So yeah, that's yeah, it's just piecing it together. When you're doing these sketch things, just think what's happening. X is 0, -infinity, +infinity, any asymptotes, anything for, y is equal to plus or minus infinity. Stick all those in. By the time you've done those, you can look on either side of the asymptote just to see which direction we're moving at, whether you're positive or negative on either side, and then that should have pretty much everything there then. So, but still, that one took longer than the other ones put together. Oh, and it is 8 marks, so you can see why that would be the case. Question 6, circle A has a radius which is 1 centimetre bigger than circle B, right? So we can, and its area is 2 pi centimetres squared bigger. Find the radio of the two circles. Right, so what have they told us with all of this then? Let's scroll down a little bit. We'll have to steal some space. Hopefully we're going to get a short question fairly soon. So we've got the radius is 1 centimetre bigger than B. Its area is 2 pi centimetres squared bigger. So we can say if we've got pi r squared is the small circle, and we add 2 pi to that, we're going to get the area of the bigger circle, which is going to be pi r plus 1 squared. So we just need to solve that for r. So we can cancel all the pi's. That's going to be equal to r squared plus 2r plus 1. So we can cancel the r squareds. We've got 2r equals 1. So, yeah. So 2r's equal to 1. So r is equal to 1/2. So that is the smaller, it's 1/2 centimetre. That's the smaller one. That's for B. So for A, it's 1 centimetre more, which is 1.5 centimetres for circle A. Okay, that was fine. And we have made up a bit of space. Part 7, 3 dice are thrown one after the other. Calculate the probability that all 3 dice give us 6. So that is going to be a 6 times a 6 times a 6, which is, what was it, 36 times 6, 216. All 3 dice give the same number. So we can have any number multiplied by the same number multiplied by the same number. So that's going to be 1/36. Only the 3rd die gives a 6. So that will be 5 over 6 times 5 over 6, because it has to be not 6's for the first ones, multiplied by 6 for the last one. So that would be 25 over 216. So they were pretty straightforward. Okay, question 8. The volume of a spherical balloon increases by 1 centimetre cubed every second. Right, so let's go back over this side. So dv dt is equal to 1. What is the rate of growth of the radius when the surface area of the balloon is 100 centimetres squared? So surface area of the balloon, 4 pi r squared, is equal to 100. And we want to get rate of growth of radius, so dr dt. So how are we going to get all of that? Right, so dr dt is equal to dr dv dv dt. So that's fine, which is, well, dv dt we know is 1. So we want a relationship between volume and radius. Okay, so v is equal to 4/3 pi r cubed. So dv dr is equal to 4 pi r squared, which is equal to 100 at this particular case. And we want to do 1 over dv dr. So it's going to be 1 over 100. That's going to be our rate of change. And that's in, what are our units? We've done centimetres and seconds. So centimetres per second. Right, so yeah, a bit of chain rule going on there. Question 9. Scroll down a bit for this. Find the area between the curve y equals mod nx, mod x to the n even, I don't know why I came up with that, mod x to the power of n, where n is a positive constant, the line defined by y equals -2, and the lines defined by mod x. Right, okay, let's come back to that one, because that seems like the pain out of it all. So y equals -2. Let's do our xy on this. So y equals -2. I'll switch over colour. There are too many lines here otherwise. So that's y equals -2 going through there. Mod x is equal to 2. So we're going to have that and that at -2 and 2. So that's good. Mod x to the n. We have to find the area of all of this. So that's going to be mod x to the n. So for what is n is a positive constant. So for positive x, everything's going to be doing that, because everything looks like that for x to some power on that side. And then we're either getting, oh, actually, it's going to be symmetrical. That's what the mod's going to do. Because if the mod wasn't there, we're either going to get the same thing on the other side if it was, say, x squared, x to the 4. If n was even, we get the same thing. Otherwise, it's going to flip down to the negative side, but we're modding it up the other side. So yeah, that's fine. Right, okay, so that's what it all looks like. Find the area between these curves and those curves. Right, so we want all of this. That's what we want. So that is going to be, well, we've got 4 by 2 in here. So we've got 8 down the bottom. So that's what we've got there. And then we're going to have 2 lots of that bit. So we've got, so the area is going to be equal to 8 plus. The reason I'm doing 2 lots of that is when we integrate this thing, we don't really want the mod sign on it. And if we've got an odd number, then we're going to get negative for the -2 to 0 bit. And we don't want that because it's just going to cancel out. So if we just take this area on the positive side, we can double it up and we don't have to worry about our odd powers or the modulus. So we want to integrate from 0 to 2 of x to the n dx, and we don't have to worry about modulus at all. So that is 8 plus 2 lots of, oh yeah, I missed the 2 out. 2 lots of x to the n plus 1 over n plus 1, 2 and 0. So what have we got on that then? So if it's 0, well, we're just not going to get anything. So we're going to have 8 plus 2 times 2 to the n plus 1. So that's 2 times x. Yeah, 2 times 2 to the n plus 1. That's right. Yeah, because I put 2 in for x. So that is, let's say that again. 2 times 2 to the n plus 1 is 2 to the n plus 2. Right, I got there in the end. Divided by n plus 1. Is that it? I think that's it. Yeah, that's it. That seems fine. Right, I'm happy with that. Right, so that's done that one. Have we got more questions? I don't normally stop on 9 from what I recall. Here we go. Right, so question 10. Sum the following series. 1 plus e to the y, e to the 2 to the y. Right, so that's a geometric series. So for the first one, we've got a geometric series going to infinity where e to the y is much less than 1. So yes, it's going to converge. So that's saying that our mod r is less than 1, which is what we want for a converging series, because it can't be negative. Therefore, we've got sum to infinity is a over 1 minus r. A is 1, and r is e to the y, so 1 minus e to the y. So that's fine. Then for the second one, what have we got here then? That's going to be, so log to base 2 of 1 is 0, then log to base 2 of 2 is 1, then 2, then, oh, it's going up in, yeah, 2 to the n, so that's going to be going all the way up to, well, n, we're just going up in 1 at a time. So we're summing up 1 to n. So we're doing, this is an arithmetic series then, which is going to be the number of terms divided by 2 multiplied by the first term plus the last term. So, you know, where we're averaging, we're pairing everything up and then multiplying by half the number of terms because they're in pairs. So the number of terms is n plus 1 over 2. Then we need to multiply that by first plus last, which is n. So yeah, so we've got n times n plus 1 divided by 2. So yeah, we've got one geometric and one arithmetic series. 11. Identify and classify the stationary points of this function. Right, this should be a gimme of a question because this is just a standard exam question really. So if that's what y is, then we've got y dash is 24 minus 18x minus 6x squared. Y double dash is minus 18 minus 12x. So we want y dash is going to be equal to 0. We can divide everything here by 6. Actually, I'm going to divide it by minus 6. Means that we're going to get x squared plus 3x minus 4 equals 0. So x is going to be equal to minus 4 or 1. So just an easy factorize, isn't it? So we've got those. So now we just need to classify. Oh, we've got to identify as well, which means we're going to have to shove these numbers back into this horrible thing here. Oh, that's annoying. So we've got one pair. So let's start with 1 because that's going to be easier. So when x is 1, we got 5 plus 24 is 29, minus 9 is 20, minus 2 is 18. And that is going to be the, oh, well, we can tell without even putting it in here anyway, which way round it's going to be. We have to have the maximum come in second because this is a negative cubic. So it's doing that. So the maximum must be at the higher x value. So that must be a maximum. And then we can say that we've got minus 4. This is the one that's going to be annoying. That must be our minimum because we've got to put minus 4 in here. So that means we've got 5 minus 96. Then we've got, what is this? So yeah, 9 times, minus 9 times 16 is 144. And then we've got plus 8 times 16. So plus 8 times 16. So that is 80 and 48, so 128. So we've got 133 minus 144 gives us minus 11, and then the minus 96 gives us minus 107. Okay, and that's our classification. So we didn't even need this. You don't always need the second derivative because, as I say, if you've got the shape of the graph, you know which way round they have to come. So yeah, that's fine, particularly if you're getting these distinct positions here. It's not like we've got some weird higher level one where we might have some kind of point of inflection or like double root or something like that. We haven't got anything like that going on in this one. So that's question 11. How many more we got to do here? Oh, question 12 is the last one. Right, okay. In the figure below, the radius of the larger circle is twice that of the smaller circle. Find an expression for the fraction of the area of the square which is occupied by the two circles. Okay, so let's mark the centers on then and get lots of radii drawn on. So let's call these ones little r. So we've got 3 touch points, put on the circle, and everywhere that the circle's touching something, we've got 3 touch points here as well. Because, where else are you going to draw them? I mean, there's no point drawing a line, over here. I mean, what's good's that going to do anyway? So anyway, you've got a touch point. So these are all what, twice, right? So that's 2r, 2r, 2r. So we want fraction of the area of the square occupied by the two circles. So we want to do big circle plus little circle divided by square. So that is going to be 4 pi r squared plus pi r squared. That's our our sum of the circles. And then now we need to find a top to bottom or a left to right. Let's go. So if we were going from left to right across here, we've got, change color again. I suppose we could go for a diagonal, but I don't think that's going to be the same effort, isn't it? Because, so let's extend that and then down here. So we've got 2r for one bit, r for this bit here. What do we know about this? Oh, we've got, well, that must be 45 degrees because we've got symmetry here. That's going through the diagonal. We've got a 3r radius, 3r hypotenuse, I mean. So we've got some triangle that's looking like this, a right angled triangle, 45 degrees on each one, which has got 3r there. So we've got this x, so 2x squared is equal to 9r squared. So that x is going to be equal to 9r squared over 2 square rooted. So the area of our square, we've got 3r plus 3r divided by root 2. And then we need to square all of that. So that seems okay, doesn't it? I think. So yeah, I'm quite happy with that, I think. So let's take these r's outside. When we stick it all in here, we're going to have 5 pi r squared divided by, well, we can actually take the 3 out. So 3r squared, 1 plus, well, so yeah, 3r all squared to give 9r squared. 1 plus, we take the 3r out, so let's make that a root 2 over 2 all squared. So we can cancel those, can make that a 2 and take that out and put a 4 at the top, which means we've got 20 pi divided by 9 times, so what's that going to be? If we square that out, we're going to get 4 plus 2 is 6 plus 4 root 2. So we can take 2's out of this because we got that on the top. So 10 pi divided by 9, 3 plus 2 root 2. Don't think we've got any more factors that I can see in all of that. No, because we've got all 3's. No, so I think that's the best we're going to manage on all of that. So that is the fraction of the area. That's quite a neat expression. That's a really nice geometry question, that one. I mean, when they give you these circles and they start telling you things about radiuses, then, as I say, mark on touch points. Draw those radii on. We could have gone with the diagonal. We would have had the same thing. We would have had two Pythagoras triangles, one down here and one down here. We could have got the diagonal on it. Because, yeah, remember, if you've got a square and you've got the diagonal, you square that diagonal, then you can see the original square has got two of these triangles, because all these triangles are the same. And the resultant one here, a square in the diagonal, has got four of them. So your square of the diagonal is twice the square. So if we had got that diagonal, which we could easily have done, we would have had this 3r plus 2 Pythagoras calculations there, square that and then halve it, and then you've got the area of the square again. But I think this is quicker going from side to side, or top to bottom. It's the same. It's that symmetry thing. As soon as you see that 45 degrees, then everything drops in. So yeah, that's those 12 questions. They're really enjoyable, the maths ones in the PAT papers, because they keep them maybe they are a little bit simpler than what you get on the math papers, obviously, because people are applying for physics rather than maths. So it makes them a little bit more fun, I think, when you're going through them.